Our next speaker is Marcelo Saba. He's a professor at INPE, the National Institute for Space Research in Brazil. He's been using high-speed cameras and auxiliary sensors to understand the physics of lightning since 2003. Since the first lightning flash recorded with 1,000 images per second, he has been publishing tens of papers in referee journals and is now recording them with hundreds of thousands of images per second in collaboration with researchers in the USA, Austria, and South Africa. He's going to be speaking on the research opportunities in lightning photography. Thank you for coming and joining us, Dr. Sabo.
Thank you. You all see my screen?
Yes. If you can enlarge it.
Yeah.
Thank you.
All right. So I was requested to speak about photography and lightning, and what we know is that from the very beginning of photography, like in this one in 1902, photographs were used to see and to study lightning with long exposures. So these photographs, they do record lightning, but the problem is that they integrate everything in one image. So everything what happens in lightning appears in one image. You can see some back lightning here, lightning on the back, lightning on top of the Eiffel Tower, but who comes first? So no temporal evolution is seen. In order to see things that happens in less than 1 second, you need to be faster. You need to see things with details with a very high temporal resolution, as you are seeing now. And this can be applied to lightning. And that was the first lightning flash recorded with high-speed camera in Brazil with 1,000 frames per second. I was amazed to see that because we could see the leader coming down, we could see the return stroke, the continuing current, and all the process in lightning, the branching with these videos. And I was amazed with that, and I started shooting several lightning flashes since January 2000. And today, we see that combining still images with high-speed videos is the best of the two worlds, because in one image, still image photograph, you can see the whole thing together. And when you see the same flash with high-speed camera, what you do, you slice what's going on in several images, and you can analyze what's happening in each branch, how things are being formed. It's a world of lightning physics and processes. So photographs, nothing else than the integration of all video frames that you can make with a high-speed video. So in photo, you have many lightning processes integrated in one image, and in high speed, you have almost the opposite. The whole lightning is sliced into several images. So coming back to that first photograph, the Eiffel Tower. So what we now believe that happened in 1902 with the lightning in Eiffel Tower was that there was, at the beginning of the flash, as you may see here, something happening in the sky. And this was a previous discharge that occurred perhaps a few kilometers away from the Eiffel Tower. And this lightning flash that happened before the upward flash in Eiffel Tower was responsible to start the upward leader, the positive upward leader that you see in this photograph. So since the first lightning flash recorded with high-speed cameras, we have more than 6,000 flashes already recorded and over 50 papers published with these images. So and to understand what can be learned from high-speed videos, I think we should talk about lightning and the process that we may see with still and high-speed cameras. This was already explained by Farhad Hashid, so I'm not taking much time on it. And you see cloud flashes, 80 to 90% of all flashes, ground flashes, upward flashes, and downward flashes. They can be also classified into polarity, negative, positive, bipolar. And here's the percentage of positive and negative that you may have during ground flashes. And also, you see downward leaders coming. You may see with high-speed video downward leader currents, return stroke, and continued currents. And then when it stops with this, when the lightning stops with the first return stroke, you usually call it a single stroke flash. But that's not usual. What is most usual is that after this sequence, after the lightning leader coming down, touching the ground, return stroke, continued current, you usually see another dart leader after the channel has broken into pieces. You may see a dart leader and then a subsequent leader that may or may not follow the same channel as the previous stroke. So this would be an example. We've been working with Tom Warner too, and this is a lightning flash recorded by Tom Warner, where you can see the first return stroke, and then what's interesting here is that the second leader tries to make another way to ground and finally finds the previous channel and follows the same channel as the first leader. And if I go further here, what you see here as the video is playing is the long continuum current that occurs after the third stroke. So this is something that's very interesting to study with high-speed videos, because you can see at each millisecond how the lightning current behaves. And the continuum currents in lightning has an important role, because that's what causes heating damages. This is an example of a positive lightning that's usually followed by this long continuum current. Most positive flashes are followed by continuum current, long continuum current, and that's why they are responsible for most heating damage that you associate with lightning. They can be a big problem for ground wires and power lines. Then it can be a big problem to wind turbines, as you may see here. So why is that positive and negative lightning are different? And the reason for the difference you can see on the way the leaders behave, because lightning is nothing more than leader propagation, negative leader and positive leader propagation. And you can see in these images how different they are. Positive leader is smooth, no branching. Negative leader, usually highly branched and very intense. You also have not only leaders, positive leaders and negative leaders in the cloud, but when they approach ground, you may see upward leaders coming from the soil, from sea, from structures, and even from persons. Here you see downward lightning striking this house, but if you look at his neighbor, there was also an upward leader trying to connect to this downward leader. As you may see here in this animation, it's a multiple flash, and when the leader is approaching ground, you may see upward leaders from the house, from the tree, trying to connect to the downward leader. And as Marianne Cooper knows very well, this may happen to people. People may be affected by upward connecting leaders, and we've been measuring these upward connected leaders with shunts and Pearson coils, and we are seeing huge currents as much as 600 amperes occurring along these upward connecting leaders. An example of an upward connecting leader is here. a video where you see upward connecting leaders from two twin buildings, 50 meters high. The leaders are also 50 meters high. And that's the whole sequence when you have, where you have to be very close to buildings to see the upward connecting leaders. They are as long as the height of the building. If the building is 50 meters tall, probably the upward leader will be 50 meters tall too. It's another example, and that's what we call the final jump, when it's defined who is making the attachment to the downward leader. As this one will do the attachment, the other one will collapse and produce current. When all the positive charge that was collected here collapses, you have a very intense pulse of current in the opposite direction. And with high-speed camera, the good thing is that you can check the size and the speed of these guys. And if you have current measurements here, you're gonna see the current too. And also you may check which parts of your building is producing upward leaders. And you see here in the detail of this image that this corner was also producing an upward connecting leader. And this is not uncommon to have a lateral discharge to buildings. And another example, where you see that the same building that's here, in a zoom photograph, you see that there's a part missing here, or here. So that was regarding downward flash. Regarding upward flashes, we've been looking for upward flashes here in Brazil, in the city of São Paulo, and we checked the density map of lightning in São Paulo, and we saw this. When we saw this hotspot, we checked what was in there. There was a mountain, and this mountain has two big towers. This is a 130 meters tower. This is a 90 meters tower. And when big systems, meteorological system, MCS, come by, that's when you see upward lightning. And that was the first one we saw in Brazil. And what we see here is that when you have negative leaders passing over the towers, you see the triggering of those positive leaders and all these recoil leaders coming down and producing M components or even return strokes. So since then, more than 200 upward flashes were collected, and we got some studies on how they behave, what are their characteristics, and so on. And the last paper was on how these structures behave at the tip of the positive leader. You see this electrons conversion to the positive leader, and you see that when the corona brush, that's the name for this streamer of currents joining here at the tip of the positive leader, when they split, then is when you see lightning branching, or the lightning formation of a very new recently discovered structure, plasma structure, that's called needles. We are now doing research collaboration with South Africa. We are also doing with Austria and some people in US. And we are very excited to do this collaboration because in South Africa, Johannesburg, you can see many upward flashes. This summer, I think we've seen already 30 or 40 upward flashes, and see also the downward flashes attaching to buildings. This is the ground flash density in South Africa and Johannesburg somewhere here, where we see these hotspots of lightning, which correspond to two big towers. And we will have a closer look at other buildings that are being struck by lightning. And hopefully we'll be measuring current. And to conclude, it's always good to have other sensors together with your high-speed camera, like current sensors, E-field, X-ray. When you join things like this, you see the combination of image and E-field, and this is really nice. To have current and high-speed videos, to have X-rays with high-speed videos, you can check when X-rays is occurring, and this is one of our last papers where we do see X-rays when lightning is pointing towards the sensor. So downward, upward, negative, positive, flashes and leaders. There's a lot to be discovered with high-speed cameras and photography. Number of return strokes, flash duration, lightning branching, return stroke intensity, time between strokes, presence of continuing current, size, speed, current of connecting leaders, production of X-rays. And these are all questions that need answers. They are of great importance to lightning protection. Thank you for your attention.
Very good. Thank you, Professor Saba. You've had to develop a whole new vocabulary for all of these different processes. It's amazing what it shows us.
Thank you.